Next thing that we have to address is so-called routing, okay? So, whenever one job finishes one service in a station that have more than one possible connection, remember that in queuing model, whenever one job finishes at one station, it goes on and enters service in another one. So we can have cases like this one, where the job can have three possible paths. It can go from this station to the one up, it can go from this station to the one down, or it can leave the system. Okay? Similarly, here, the jobs can decide to continue to this station or to leave the system. And even here we have two alternatives. The job might continue to the service below, or it can even return to the same station and do another pass to the same service, so repeat the service at the same station, okay? Whenever we have several alternative routes that our job can follow, once it has finished service, we need to specify in which way we can model the choice of the next station, okay? And this is called the routing policy, okay? Of course, a routing policy is required only when we have more than one destination, okay? Stations like this one, where we have only one possible alternative, jobs that finish from this station must for sure goes in this direction, as well here. Job that finish here can only continue and re-enter this station over here. They do not need a routing specification. Okay, so let's see which type of routing we have. First of all, we have to understand why we do routing. Okay, routing can essentially model two things. Okay, in one system where we have some alternative, like imagine that we are in a mall and we have some shops, then we have some cafe, and we have some playground. Okay, each time we leave one of the area, we choose the other. These models the fact that we want to spend some time in the system. During our activity, we are going to do several things, and the several things we are doing can be characterized, deciding whether after the cafe I will go to the playground or to another shop is something that describes the life of the jobs in the system. Okay? Another thing is if instead I'm considering the lane at a supermarket. When I am arriving with my cart, I will have to decide which one to join. Okay? In this case, the different service are some alternative moving. Here instead we are continuing, but we have some guidance in the choice. Usually we will join something that is smaller than the other, okay? So one thing is if the next station is really something that completely does another thing, or whether we have to choose between possible alternatives to obtain some goal. Now, probabilistic routing is used whenever we have to do a set of activity in our model. We do not know exactly which activity we are going to do next. Depending on each job, we might go to a different department, so we can have we can embed a decision of which will be the next stage our job will be doing. Okay. In this case, we usually use the so-called probabilistic routing. Okay. In probabilistic routing, each exit path from one station has assigned a probability. In this case, 0,2 for route A, 0,5 for route B, 0,3 for route C. The probability sums up to 1, okay, because it's a probability distribution. So basically, we toss a coin after we have finished from this station. We toss a coin, and depending on the value, we will join either station A, B, or C, okay? This is useful because we can, by appropriately setting a value, we can match the flux of jobs that moves in one system. In particular, one of the ways in which this can be done, we can count all the jobs that finish from this node S. The completion at S is already one of the parameters that we have always used here to compute the throughput, the average service time, etc., etc. But then we also count how many of the jobs which left station S arrived in station A. How many of the jobs that left station S arrived in station B? How many of the jobs that lived in station S arrived in station C? This is what I called ASA, ASB, ASC, means the jobs which arrived to station A coming from S, B coming from S, C coming from S, which might be different from the number of arrival to station A, B, or C, because remember that each of these stations might also have input coming from some other nodes, okay? So the number of arrival would include the jobs that arise from here and for there, but ASA will only include the arrival from this point, okay? If we are doing this, we know, for example, in this example here, that the completion at node S will be split as the arrival to node A plus the arrival to node B plus the arrival to node C, okay? Because the job won't vanish during the route, and they will either join after S, A, B, or C, okay? If we have this count, we can compute the probability of making one choice as the ratio of how many jobs went directed to station A with respect to the job that finished from station C. And this means that, again, applying techniques very similar to the one that we made in the beginning of the course, analyzing logs file, we can evaluate this probability analyzing logs of the system, okay? This is the probabilistic routing. If instead we want to model some intelligence on some way in which the jobs select a possible next station which provides an identical service to parallelize some sort of jobs, so in a scenario like the one of the cashier, where the user somehow will choose which of the cashier we want to use, or in case in which we have some sort of web server, okay, we have a request and we decide whether to route it to the web server on the top or the web server on the bottom, okay? In this case, we want to model the choice as a way of increasing the performance of the system by replicating some component and allow the jobs to choose the component. Probably probability will not be the right choice, because even if I put, for example, that, okay, the two are equivalent, so I will join with 1/2 probability either of the two, okay, this will not be really realistic, because randomly choosing this might be that 10 jobs in sequence will choose this one, and later maybe 5 will join the other. So it doesn't really guarantee that we uniformly split the jobs between the available services, okay? For this reason, there are other routing policies. Two of the simplest to understand and most important are the round robin and the join the shortest queue, okay? So, round robin is the classical type of policy that is used whenever we are trying to model things similar to a load balancer in a web server, okay? This queue might represent the web server. This might represent the load balancer. So, round robin will make sure that every job that finishes at the load balancer will choose in a round robin fashion another queue. So the first job will go to the station on the top, the second job to the station on the middle, the third job the station on the bottom, the fourth again the one on the top, the fifth again the one on the middle, the sixth again the one on the bottom, the seventh the one on the top, eighth the one in the middle, ninth the one on the bottom, 10th the one on the top, etc., etc. All the alternative completely rotates one after the other. Okay? In this way, the load is balanced in a more even way than just telling that each of these has 1/3 of probability of being chosen. Because if we said that there is 1/3 of probability in being chosen, it means that we actually toss a coin without knowing anything, and due to the result of the coin toss, we choose one of the other services. While when we select this round robin, we are sure that only after 2 customers this will be used again, because the next one will go to different stations, okay? Which might be more efficient from a balancing point of view, and it might be more similar to what a real load balancer does. Okay. Again, this is the classical thing used to model how requests on the internet are split. For example, the rotating DNS is one of the classical ways in which you actually use several web servers in alternative. And that's the reason why if you use the trace route to Google, you will see each time a different address, because the load balancer will send your Google query to a different server every time. Okay. Join the shortest queue is instead an intelligent policy, again used for balancing the system, and in general is the one that you probably will use for modeling something like a supermarket, okay? Here, once service has finished, the user has the power to query the length of the queue of the stations ahead, okay? Once it knows the length of the queue of the service ahead, it will choose the one with the shortest queue. Of course, it might happen that there could be 2 queues that have exactly the same size. In that case, it will choose the one that is random. It will choose randomly between the one that have the minimal size length. Okay, and this is the classical case where we have parallel services, each one doing exactly the same thing, and users have the possibility of deciding which of the 2 might be chosen, hoping to have a shorter response time. Okay? This can have an impact on the model. For example, here I created a system. I put one service here, then 2 servers, one with an average service time of 3.5, another with an average service time of 1 second, and the probabilistic was the one having the worst possible performance. Round robin was slightly better because it was never sending 2 jobs here. The probabilistic, whenever sends 2 jobs in a row or 3 jobs in a row to this station, it will overload this station, and so it will make it extremely low with a really long queue, while round robin will never send 2 jobs to this same station, so have slightly more a quicker behavior. This probabilistic here is something that, let's say, balance the request. For the one of you that have done computing infrastructure, know that very nasty exercise where you have to balance the request. Here, requests have been balanced by the 2 servers so that they are equally utilized, and it's probabilistic, but you have more probability of joining the queue in the bottom because it is faster, and only a smaller probability of joining the queue on the top, okay? In this way, the service time is much better because the response time is much better because you will not overload the queue that is very slow, but yet not optimal because due to the probabilistic way, you might still send 2 jobs in a row to this system, or you might send too many jobs here and actually overload that node over there. And the join the shortest queue is the one which has clearly a winner, a very nice performance, because every time we'll always join the queue with the shortest, the station with the shortest queue. So this will be joined probably only when it is empty. And however, still joining it when it is empty, it will reduce the load on the other one and thus increase the service time. Okay? When we are modeling a system where we have several alternatives, it becomes thus very important to select the correct routing policy. And this depends on what these services are. If those are 2 parallel execution, which can both service our request, then probably the round robin or the join the shortest queue will be the best one. Otherwise, if we are imagining that the 2 services are alternative, so here this is the reception. These are 2 possible things that you want to do at the post: send a package, pay a bill. In this case, the routing go to the department that sends the package or go to the department that let you pay the bill depends on what the user wants to do. So it cannot be neither round robin nor join the shortest queue, okay? Because it depends on what you have to do. But in that case, you usually can, once stood in the system, check on the frequency how many customers needs to send a package, how many customers needs to send a bill, and by properly doing this ratio, you can compute the